Good.
My name's Irene Wallis. I'm in New Zealand. I'm a geothermal geoscientist, so probably a little bit adjunct to this group, but I'm thrilled to be invited. Um, I am a structural geologist by bent and a borehole image analyst, and I've taken the cheek of actually putting up a slightly different talk than what was advertised, in the hope to spark a little bit of community discussion. And so we will look at the Ramsey 1, Ramsey 2 natural hydrogen content as a case study, but I've couched it a little bit different inside a wider discussion about fracture width and fracture aperture in borehole images, both types, acoustic and micro-resistivity. And I'm looking forward to hearing from the community. Going to throw out a couple of challenges. Alrighty, let me see if I can get this pointer. Right, so this is a general outline. We're going to start making sure that we speak the same language. We cross lots of time zones and lots of disciplines. So we'll start with a couple of definitions and talk about why we might care about aperture or width. We'll have a look at the methods that I've been using. I would love to hear from the community if there's anything else. And we'll look at some case studies from geothermal and from natural hydrogen, and then we'll wrap up from there. So width versus aperture. Let's pop that over there. So in a fracture, like a mineralized fracture will still have width, a distance from the top surface to the bottom surface, but it doesn't have an aperture, so it doesn't have an opening. If we look on the right-hand side here, this fracture has both a width from the top and bottom surface and also an aperture, and they're not necessarily the same values. If we didn't have this nice druzy quartz in here, we'd probably have the same width and aperture on this one. So we're going to talk about both width and aperture in different contexts. But both width and aperture, these measurements really help us with geologic insight. So essentially a borehole image analyst is logging an outcrop with horse blinkers on or a section masked off with their nose pressed up against the outcrop and picking every single little crack that you can see. And normally when we're out in the field mapping structure, we stand back from the outcrop and we think about what is the big features. And it's very difficult if you view all of the data on the same scale, the little features and the big features, it's really difficult to see what's big and important and what's less important. And so these are two stereo nets with the same data. If people aren't familiar with the stereo net, it's a way to project fracture data. Poles to plane is what's shown here. It's a way to project fracture data so you can see it all together, like both its orientation, its strike, and its dip. And the left-hand stereo net is how we typically see borehole image data projected. All the markers are the same size. But on the right-hand image, they're actually scaled by width. And we can see we have a bunch of low-angle features that are actually dissolution caverns that are very wide. So the larger the marker, the wider the feature. And we've also got this population that's dipping to the northwest that also has much larger width than the rest of what's there. And so the idea is if you're tracking width, it gives you that opportunity to be like a field geologist and step back from the outcrop a little bit. I work in fractured reservoirs mostly, and so what I'm looking for is the structural trends or individual faults and features that are likely to influence the fluid flux. And I want to be able to define the magnitude and distribution of secondary porosity, but that's pretty aspirational, and by the end of this you'll see why that is very aspirational, but we hope to get there one day. We're going to start, however, this talk with a little bit of a digression that talks about this grey shaded zone on the outside of the stereo net. So you see where there's less data on the outside of the stereo net, I've shaded that grey. And that zone, by Ruth Taziki in the 60s, was referred to as the blind zone. And so that is an area where, because of the way the well goes through the subsurface, you have a diminishingly small probability to intersect fractures. So these are poles to plane on stereo nets. We've taken a borehole, or essentially you could do a scan line as well on an outcrop, and we've drilled that 1D line through the subsurface. And that 1D line through the subsurface has a very low probability of intersecting fractures that are parallel with it, and very high probability of intersecting fractures that are perpendicular with it. And so on these plots, the triangle is the well path, and fractures that are perpendicular to the well plot around that well path, and those that are parallel plot in, I'm not sure if all countries of the world think of cricket, but it looks a bit like a cricket ball, plot in this sort of seam area around the cricket ball inside the blind zone, about plus or minus 17 degrees from the well path. And so it generates this persistent gap in data. So we've got 1, 2, 3, 4, 5 well case studies here, and we can see this influence that it has on the population. But we do have to remember, as we see from this Fish Lake example, this is a deep circulation system in the US, wellbore deviation can change through the logged interval. Often I'm just going to show you a mean, but here we've got a wee population of fractures that are inside the blind zone, and actually they relate to an area where the wellbore deviation was different. So if you see a little bit of that cross-matching, sometimes it's because of walk in the well deviation. And I think the thing to also take away from here is Ruth linked her name in that paper to a correction, the Taziki correction, which is so often embedded in many softwares. It's a weighting that for the most part, and if you're close to, sort of the bullseye area of the stereo net, will somewhat correct for the distribution of missing fractures. But because it's weighting, if you haven't sampled any data, there's no weighting that can be done, and so it'll never actually resolve the blind zone. The blind zone becomes this persistent gap that we're best just to be aware of. Right, back to the topic at hand. I work with both acoustic and microresistivity logs. Lately, a lot more microresistivity borehole images. So they measure electrical resistivity at or just into the borehole wall. And it's a relative resistivity. So fractures are seen as relatively more or less resistive than the surrounding host rock. And so here we have resistive fractures, examples of resistive fractures that are filled with minerals that are more resistive than the surrounding host rock. Fractures that are relatively conductive are most likely to be open, but they're not always open because they could contain mineral fills that are more conductive than the surrounding host rock. And in my world, they're typically clays. So I'm more often than not working in volcanic hosted conventional geothermal systems. And so in this example here, which is a monster of a feed zone, so 39 tonnes per hour, for context, a standard total capacity for a geothermal well may be sort of around 5 tonnes per hour per bar. This is one zone, one set of fractures that is taking a massive amount of fluid. And these conductive fractures really are open. And part of the indicators of that being open, they have this like edge blurring effect. The fractures often interact with drilling-induced damage, so you get tensile fractures that hook into them, this whole path of least resistance through the rock of any breakage. And also in this case, the reservoir engineering data shows that there's fluid flux in and out of this zone. But it is also important that when we do get features that we're fairly sure are open at the wellbore wall based on a number of indicators, the hoop stress, and especially in my world where the thermal stresses can be very great, you can actually get something that looks open at the wellbore wall, a parted discontinuity that 1 to 2 borehole radii back, it's not really open at all. Looking at microresistivity data and acoustic data together, or acoustic data alone, actually in some cases, can be extremely valuable. Because where microresistivity data has that pad in contact with the wall that's measuring that resistivity, acoustic's sending a wave out and that wave return comes back. Or in the case that that wave return is lost into a fracture, it may not come back to the receiver at all. So this image here is from one well, it's one interval, it's on depth. On the left you have your microresistivity, on your right you have your acoustic, and it's got an amplitude, which is the change of that wave height as it comes back, so after it's bounced off the wall, and then a travel time. Noting that the travel time data is actually plotted backwards here, so your normal dark colors are actually light colors here. So this well is also double the bit size, so the tool is sitting on the low side, so there's this little patch of data that we're just going to ignore. And so here we see a blurred fracture in the microresistivity image that has this really nice travel time signal indicating that it's open, and here's another fracture and a nice signal indicating it's open. So having these two kinds of data together are really very, very useful. But we really want to quantify aperture. And there's a nice piece of research done in the 90s that's now an algorithm in a lot of software packages, the Lutfi and Sophie method, that uses excess current flow. And the algorithm is based on this model that maps the additional current flow to an aperture, given that you know the resistivity of the mud and the resistivity of the invaded zone. What happened during their research is they had their measurements, and then they calibrated this coefficient, this exponent, until their model results fit their observed. But unfortunately, because we don't know what it really is in the subsurface, we don't have that luxury to do that kind of calibration. And so there's a certain amount of uncertainty in how, how these exponents are defined and coefficients. I would love to hear from the community what various rules of thumb are or successes people have had, but I've found it a little bit touch and go. I also find the method a little bit opaque because I'm one of those people who scripts codes a lot, and I often want to see how things are implemented. And that's not something you tend to be able to see if it's built into software. I work in geothermal. It's extremely unusual to acquire petrophysics for various cost reasons, more often than not. And so the ability to have an image that's been relative resistivity that's been calibrated to invaded zone resistivity is pretty unusual. We've touched on the user-defined coefficients being a bit of a challenge. And one of the things that I've noticed is that the actual results tend to track with overall invaded zone resistivity. This example here is from one of the Ramsey wells. Sorry, I didn't put a citation on that. And it's not a particularly strong example. I have seen stronger examples. But here you have the resistivity. And so when the resistivity is high, the values for aperture are low, and when the resistivity dips down, the values come up and then back the other way. In some cases we can make a geologic argument for that, but I've really have seen situations where you can't make an argument for that. And it looks like a little bit of an issue inside how this method's been implemented. A second method we could employ is to define the width. It's also fraught. And with a manual width quantification, you're essentially, as an analyst, mapping the distance between the two fracture surface in a click and drag kind of way. And then a geometric correction needs to be made for the angular relationship between the fracture and the borehole to go from an apparent width to a true width. This method is definitely more subject to the experience and judgment of the interpreter. It is very challenging to just fit one width and sinusoid to complex geologic features, as we'll see some examples soon. And so mixed fractures or very non-linear fractures can be poorly defined by this method. But where we're trying to get that set of relative values so we can step back from the outcrop, this can still be very useful. So we're going to look at a couple of case studies that shows where this is used and how it's been used, and the challenges with doing this with an aperture quantification. Some overall themes that we're going to pop out at the end so we can watch them come through. The modeled aperture and the manual width results differ, especially for large fractures. Width analysis reveals geologic trends, and wide fractures correspond with evidence of fluid flux in some cases, but not all. And that's very much a thing of any fluid flux is controlled not by just what we see at the wellbore wall, but connections to a wider reservoir. So this is in a limestone unit. On the left-hand side, so it's the same dynamic image twice over, dynamic normalized image. And on the left-hand side, we have the results of the modeled aperture projected with the modeled width and the manual width on that. Now, issues of additional sort of current flow, I've seen sort of smearing as you get closer to images, issues of the maybe the actual thickness, that sometimes images that are sometimes fractures that are very acute to the borehole tend to look wider, and that may be also in places fractures that are very acute to the borehole suffer a bit of damage as the pipe goes past it, and so you grind off those edges of the fractures. All of these are problems with manual width, and but I, like each of these methods has their pros and cons. These are bedding parallel fractures, poorly named. They're not really fractures, they're dissolution cavities in limestone. And yeah, so the modeled width of these is, the modeled aperture of these is very small, and the measured width, you sort of, it's relatively straightforward to pick the top one, but how are we going to pick this lower one here? You're really having to make a call for what that might look like in your final data. So you're going to see two plots on the same scale, manual width, modeled aperture of the same data. So thanks to Gold Hydrogen for letting us share this. Dr. Andy Wilson and myself worked on these wells. They're natural hydrogen wells. And so we're looking here at a cumulative width. Don't worry about the dashed weighted lines right now. Cumulative width in the black and the modeled in the dashed line. And so you see the modeled in general is much smaller. But as I toggle between these two figures, I want you to keep an eye on these bedding parallel, mostly dissolution cavities like this one here. So here is the excess current model results with aperture, back to width, back to aperture. So we could argue perhaps that that the aperture of these features is narrower than the actual width, but in a lot of cases when these data are projected back on, we can see that they really are much wider than the upper limit of the model. And the original authors, Luke and Sophie, talked about if you read their paper, they talked about their approach being valid for very narrow fractures, but don't say anything about the validity for very wide apertures, large apertures. So this may highlight that we need to look at other methods to find an actual aperture for the larger methods. And in the meantime, manual width may give us a better understanding of the relative distribution. Both results give us something along the lines of what we'd expect. They're log normal with some truncation bias at the low end, as you'd expect from a tool with resolution. The difference between the two data sets, and I've put this on a semi-log plot, is the tail of the manual width. And so there were 20 fractures that had widths greater than 30 mil, which is past the upper limit of the model. And these wide fractures are at the same depth of where the hydrogen peaks were in the mud gas. And so in terms of converting our borehole image analysis into insight and being able to stand back from that outcrop and understand it, understanding where those very wide features is useful. And so here we are. We saw these right at the start, these low angle large cavern features here, and here they are with the peaks and the mud gas where the large caverns are. The other thing, and just sort of highlighting again in terms of that geologic sense, is that we've got sort of two high frequency populations here of fractures. And you'd think, the triangles of faults, you'd think you've sort of had similar importance between these two populations. But when you look at the width of them, really the population here dipping to the northwest has these are upper hemisphere, northwest have a greater width and are likely to be more important in terms of reservoir processes. So we're switching case studies now. How are we doing for time? So we're going to look at the results of an acoustic borehole image from an EGS geothermal project in Newberry. Thanks to Alterock for providing this case study. Because it's an acoustic borehole image, I've split the data by is visible in the travel time, so likely to be open, and that's our squares, and not visible in the travel time. So you have both low amplitude and high amplitude features. And so you see that there is sort of two populations, there's a bit of a trend, there's wide features in both, but the red lines here are where they got a little bit of drilling fluid losses, and really we've got these clusters of wider, likely open fractures and a very large singular fracture associated with those fluid losses. But as I said before, here's a very wide, likely open fracture, but there is no fluid losses with it. So some, but not all cases, depending on reservoir connectivity. And again, circling back to that idea of like making geologic sense. If you took a frequentist approach, like just looking at the frequency of the green markers, so the squares and the circles, you'd think that the population, these are lower hemisphere sterionets, so this is an east dipping population. You'd think that that was the most important population, but it looks like most of the wider, likely open fractures are south dipping. And so you see them here. And so that's an example of plotting the widths helps tell you an extra story. So what do we see in these case studies? Essentially, the excess current model may underestimate the largest features, and we should sense check that against the image. The original work validated it up to some very low apertures, I think. I'm trying to remember, it's 0.4 or 4 millimeters, but it's very small. Width analysis results corresponds to evidence of fluid flux in some, but not all cases. And we've always got to think of reservoir connectivity. And just looking at fracture frequency may not tell us the whole story. We need to step back and think about what are the largest features, what are the most likely open features. Like any analysis, if we can use multiple approaches, our interpretation confidence increases greatly. So using an acoustic and microresistivity together is ideal. It gives you both that geologic context from microresistivity, all of those textures, the ability to understand why you have fractures in one place and another, and then with the acoustic, that travel time data becomes invaluable for those of us looking for the big fractures. And then modeled aperture and measured width. Let's do that together. And I think I wanted to really emphasize that we should include attributes and bias in the way we plot our data so that we can increase our interpretation value and avoid misinterpretation. And so that's like the issues with the blind zone, understanding confidence of different features and so forth. So I'm hoping there's lots of other image analysts here, and I've proposed some maybe next steps of what we could be doing to help us improve in this space. And so first off, we can sense check our results, taking it, projecting it back on the image and thinking about, okay, is this really systematic with what I see? You know, let's ask critical questions about any data biases. You know, like that issue with it appears that modeled aperture is varying with that invaded zone resistivity. We need to state really clearly what is being measured, and that's something that I've been not great at in the past, and I've really only recently started getting quite firm about splitting width and aperture. And let's really say what the methods that are being used and their uncertainties. And we just can't assume if an existing method is out there, built into software, or just because the person sitting next to me uses it, it doesn't mean it necessarily works, and we should conduct validation studies and share them. And in that vein, any support to frontier research into finding other methods for quantifying fracture aperture would be amazing. This, I think, is the holy grail, particularly for that big end, in my view. And then combining these analyses with geomechanical modeling. I've sort of bombed into this section, but I must say I've done a bit of that myself. I don't have anything that I'm allowed to publish as yet, but it really does make these divers sing. And I'd like to hear from others as to what they think they should do. This kind of work isn't possible without companies who share data. Gold Hydrogen recently with the Ramsey cases, Alter Rock with Newberry, and then you saw some other cases that come from my doctoral research, Supreme Energy, Contact Energy, Mercury Energy, and Open Mountain Energy provided the Fish Lake case, which is published at a conference a while ago, and then collaborators, Andy, who I collaborate with regularly, and Julie Rowland, JR, and David Dempsey's, who's both contributed to this work over the years. There's some citations for the enthusiastic people, but I'd love to know if there's any questions. Peter, should I unshare?
Thank you. You should be able to unshare from the button at the bottom of your screen. Everyone is able to unmute themselves, but before we do that, we have a question from, I hope I pronounce his name correctly, Makaba, who says, I was just wondering, what do you mean by low amplitude and high amplitude fractures? Are they similar to open and filled fractures?
Great question. Great question. High amplitude and low amplitude would be like if you walk up to an outcrop of basalt and you hit it with your rock hammer, it makes a high frequency sound. Bing. If you walk up to an outcrop of not very hard sandstone, it goes thud. That is the height or the sound or the amplitude of the wave coming back to you. You could get a low amplitude fracture that is filled with a soft mineral. So it's not necessarily open. You can get closed low amplitude features. It's the travel time that's diagnostic for openness. You know, like where you lose waves into those cracks, plus or minus scattering of surfaces.
Thank you. Do we have any more questions? Please feel free to unmute yourself and ask a question. We have a question from Roberto Berto. Do you think that on these kinds of geological frameworks, geothermal high empathy, could be useful some purely lithological logs in order to discriminate between real open fractures and clays, which are infilled features?
To clarify, when you say pure lithological logs, do you mean like petrophysical logs?
Roberto?
Yes, I mean to discriminate, for example, if you are in front of really conductive fracture. I'm speaking about a resistivity image log. If you think that it's possible to combine, for example, high sampling rate gamma ray or a spectral gamma ray to try to discriminate if there is an infilling material, a clay infilling material using, for example, I don't know, some
That's what we use.
indicator.
Yeah.
Yeah, if you can use
Right.
this kind of approach to help the imaging interpretation, is this
So
if you
where
in
there
your
is
environment? Yeah.
where there is petrophysics, it's extraordinarily valuable context. But we have this issue of, like when you have particularly places with complex overprinting paragenesis, like high enthalpy systems that have waxed and waned, a lot of clays. It's very difficult without actually seeing the textures, seeing the image to work out, like what could be just old fractures and disseminated alteration and fresh. I'm yet to see. I think some of the high resolution azimuthal gamma may provide some frontier help. I've seen, unfortunately, we have very poor borehole conditions. They're often quite rigorous,
Okay. Okay.
oversized. They don't work too
Okay.
well. Sorry.
Okay, no. Okay, okay. I have some experience working in some carbonate, but in presence only of okay calcite, where suddenly the presence of an increasing of thorium, if you have. For example, residual shales, where it's possible, try to combine the not a gamma imaging, but a spectral gamma, just the single curve, to couple this information with the image to try to detect if the darkness of the fracture could be related with opening, or to be is possible to relate this darkness with a clay infilling material. Have you
I think
understand
it's
my point?
great.
Yeah.
Yeah, I think it's a great idea. I haven't seen it done. Um, yeah,
Yeah,
like
something
if
possible in
it's
your
yeah,
in
it
your
certainly
geological. Okay,
it
okay,
certainly sounds possible, but I've not seen it done. I'm so sorry.
okay. Thanks a lot. Thanks a lot.
I think someone
Okay.
has their hand
Yeah,
raised.
Saeed, you had a question. You want to unmute yourself and ask your question, please?
Hello, this is Claudia speaking. You hear me? Yeah, hi. I'm sorry, I have no camera. I sent a question over the chat, but I want to rephrase this here. And I was working on electrical and acoustical and also optical borehole image interpretation. And I was thinking, would this be helpful measuring an optical borehole imager? Because I know that the image itself, it's like a photograph, to help in distinguishing clay-filled fractures versus open fractures, which is maybe hard on the electrical survey or the electrical borehole imager. And also, it looks really as if you stand in front of an outcrop. It's so beautiful. And I was thinking, do you have experience in that?
So I'm yet to see one optical image in my sphere, but the majority of my work is over 240 degrees Celsius, and we just run tools under injection so that you can log standard oil field tools, keep the well cool enough to do that. I haven't eaten any tools yet, which is good. I'm wondering if you can tell me the temperature limit of an optical tool.
I don't have the, this is an ALT tool from the company in Netherlands. I need to recheck that. I need to send it back, but it was from that company, ALT. I think it's called
I know the
Advanced.
guys there well.
Yeah, okay, yeah, you know them.
Okay.
And it was,
I hadn't considered it, and no one's run them in volcanic geothermal systems that I know of.
mhm.
Um, it's a
Yeah,
great
it's,
suggestion. Yeah.
you know, it is from the story goes like that. We have in Austria, we have a tunnel. We prepared for tunneling as a project from one side of the country to the other through the Choralm, which is a big mountain actually. And we had there at the top of the mountain a very deep borehole. So it was about 2,500 meters, not kilometers. And they looked there these optical and acoustical borehole imagers because they wanted to really be sure that the water is not due to this tunneling just vanishing, you know, that the groundwater is still there, and they wanted to know about the fracture system, and this was really not high temperature. But the quality, so this was a water clear mud, so you really can see very clearly when you have a mud contaminated with something, it likely is not that clear. But this is my actually suggestion to maybe this could be an advancement in that, yeah.
If they can handle the temperature, it would be great. So geothermal wells tend to be drilled under. You hope you go to total no return, so nobody bothers dumping mud in the tanks once you get to that point, and then
I
you
see.
just spot a high vis a polymer while you're making a connection. So we tend to acquire really beautiful images. We've got quite clean boreholes, no mud filter cake, nothing like that. So it could be suitable, but my only concern would be temperature, and I don't know much about it as a tool. So
Yeah, this could be a constraint, that's true. But from my experience, we then, when we have affirmated or interpreted and fractures, well, we always need a dynamic cross-check with noise logs, flow meter logs, well tests, to really get the reasonability check on this, and also work a order of magnitude higher to get a KH and to reference that back. I know that's then a little bit, this discrepancy, but somehow included, yeah.
Integration with reservoir engineering is the key step. You know, like you take these images and then you integrate with the reservoir engineering, and I think that's where the real value comes about. You know, like sort of running those pressure temperature spinner logs, looking at the permeability, looking at the like the actual permeability away from the wobble wall.
Yeah, we are
That's
searching for
really
dynamic,
exciting.
yeah.
So,
Okay, thank you.
Okay,
great
thank
suggestion.
you, Irene. Great talk. In the interest of time, we do need to move on to the next talk, but people can continue to ask questions in the chat, and I'm sure Irene will answer them there.